Yeah, go ahead, Tufik.
Yeah, okay. Good morning to everyone. Yeah, I'm Tofik Yakubu and I'm from Ghana, and I'm in the diploma session in ICTP Italy, and I am reading Earth System Physics. Thank you.
Great. Anybody else?
My name is Belbashir Taraq. I'm from Algeria, and I'm a student of ICTP diploma here in Trieste.
Great.
I'm Simone, and I'm a PhD student from the University of Trieste.
Mm-hmm. Perfect.
Hello.
So we have 8 participants and
Hello.
Hello.
Yes, I'm by names of Innocent Ategekimana. I'm doing a master's in geophysics at ICTP IFAR.
Okay, great.
And it is in Rwanda.
Perfect. So others?
Dung, are you there?
I guess we have Dung.
Dung and Kumsa.
Yes, okay. Okay. Hello everyone, my name is Dung. I'm from Vietnam. I'm diploma student.
Mm-hmm. Perfect. So I guess we have Kumsa. I don't know. So I don't know if he or she is hearing us.
Kumsa, are you there?
Okay, by the way, we can start. So seems that 3 of you are from diploma program, right? Okay,
Yes.
great.
Yes, yes.
So this is the topics, I mean, the list of the topics that we are going to talk about today. And the general, there is a very good review paper. I guess you can see the front page of the paper now, right? It's
Yes.
Yeah, it's published on 2003, entitled Earthquake Ground Motion Estimation Using Strong Motion Records, a review of equations for the estimation of peak ground acceleration and response spectral ordinates. It's an amazing review paper, and almost everything that we will discuss during this lesson is from this paper, and you can read it, and it's amazing. And there is another more recent paper by the same author, John Douglas, which is published on 2016, and it's a more recent review of the ground motion equations. So the topics that we will cover today is a short introduction, then we will discuss the strong motion parameters, type of ground motion prediction equations, data selection criteria, correction techniques, combination of horizontal measurements, separation of GMPs into source, path, and site dependence, characterization of source, characterization of path and site, and finally, analysis techniques. And as I told you, you can find all the details of the materials in this paper. So this is the planet that we are living on, the blue planet Earth, and we built some infrastructures and the structures on the Earth, and a phenomena called earthquake is happening on some places in the world. So when an earthquake occurs, it can affect our structures and infrastructures, and we study this phenomena. We study the earthquake and its effect. So generally, we can split the earthquake-related studies to different branches. So one of them is earthquake seismology. And we can say that the earthquake seismology is somehow related to the deeper structures in the earth. And the other one is engineering seismology, which is the topic of this lesson. And it's somehow related to the ground motions caused by earthquakes at the surface or very near surface on the earth. And the other field is called earthquake engineering, which concerns about the effects of the earthquake on our structures. There are some other fields of study also that, for example, one of them is structural health monitoring, and this is more related to it's pure engineering. So this is just a figure of the earthquake-related studies to have an idea that when we are talking about earthquake seismology or engineering seismology or earthquake engineering, what those fields actually mean. So, as I said, we have earth sciences that is mainly related to earthquake seismology, and we have engineering that are mostly related to the structures. And engineering seismology is actually the link between earth sciences and engineering. So the question is that how can engineering seismology link earth sciences to engineering? The answer is that it provides some information as input for engineering design. One may ask that what is the main input of engineering seismology in engineering design? So the answer is that it provides the loading conditions. And one of the methods that can be used for estimating these loading conditions is through equations based on strong motion recorded during previous earthquakes. So these kind of equations are called ground motion prediction equations, or GMPEs. And so here is an example of a very simple example of the equations. The numbers are not important at all, but the most important point here is that we have independent parameters in this equation, and we have a dependent parameter and some coefficients, as you can see in this equation. So the independent parameters of this equation, one of them is earthquake magnitudes, which is shown by M, and the other one is source to site distance, which is shown by R here and here. And the dependent parameter to the left side of the equation can be peak ground acceleration and spectral acceleration. So these kind of equations in the literature you may face, I mean, they can be represented by different names like attenuation relationships, attenuation equations, or ground motion models that sometimes they mention it as GMMs. And so these equations will finally be used in probabilistic seismic hazard analysis or deterministic seismic hazard analysis to provide the engineers with the loading condition for the structural design. So the complete procedure for driving GMPEs can be summarized as follows. The first step is to record earthquakes using strong motion instruments to get a set of records for analysis. So here you can see an example of the earthquake ground motion, strong motion networks in Iran. So these black squares and red triangles are two different types of sensors. And you can see that, for example, in a country in Iran, there are too many of them, but it's never enough. So it's not like seismometers. So we don't need such a dense array of seismometers. And but for strong motion instrumentation, it's never enough to have the enough number of instruments. So there are this network, Iran Strong Motion Network, as an example, has been operational since 1973, and the maximum peak acceleration of 1G is recorded by these stations. So here you can see some examples of accelerometers or strong motion sensors. To the left, these two are one of the more sophisticated and sensors that are developed recently. And here you can see another one called SSA2, which is an old one, but it's digital. But as I said, for example, this network in Iran has been operational since 1973. So the old instruments are actually similar to this one, and they are analog. They are not even digitized. So considering this point, nowadays it's almost done, and it's very difficult to find analog sensors in the field, and they're probably mainly in the museums. But if you have some analog sensors, and if you want to use the records of last earthquakes, I don't know, some old earthquakes, you need to digitize the analog records, but it's probably done everywhere in the world, so you can just simply neglect it. The third step is to process the digital records to eliminate shortened line period noise. Then we can select and calculate the dependent variables from strong motion records. And next step would be to collect the independent variables of the equation, like magnitude and distance and site, and we will discuss it later on. The next step is to perform regression analysis to drive the equation and calculate the standard deviation, the uncertainty, and we will finally use it in, as we already said, in probabilistic seismic hazard analysis or deterministic seismic hazard analysis. Just to be sure that you're hearing me well, or?
Yes,
Okay.
it's cool.
Yes, yes.
Okay, great. So, so as I said, to the left side of that equation, we need some strong motion parameters. And the most common strong motion parameter is peak ground acceleration, and it's useful for analysis of short period structures. So here you can see an example of the strong motion records. It's shown by red. So it's acceleration. It's showing the variation of acceleration with time. And so can you tell me that where the PGA is, because it's the simplest strong motion parameter. I want you guys to interact. Is this the circle is showing the PGA, right, or not?
Yes, PCI, because we can see a higher amplitude.
I think that the PGA could be the lower peak.
Oh, the negative peak.
Yeah, the negative peak, because
Exactly.
in modulus it's bigger than the one where the pointer is right now.
Yeah, exactly. So it's not that simple. I mean, it's quite simple, but it can be a little bit tricky to recognize that. And so it's actually the maximum of the absolute, you see? And then, so the other strong motion parameter is called response spectra. So I said that our buildings are affected by earthquake, and engineers, structural engineers or earthquake engineers, they expect the loading condition to be provided by engineering seismologists. So one of the most important parameters that we can estimate is called response spectra. So we can simplify our buildings to a simple degree of freedom system, and the result of such a simplification will be a system of mass and with a spring and with a damper and ground. So here you can see that UTT, which is the acceleration, this is ground acceleration. And we have the mass here, and we have a string with a stiffness of K and a damper with viscous damping. So from Newton's second law and resolving the forces horizontally, we can reach to this equation here, which tells that if we multiply mass by acceleration of the mass, not the acceleration of ground, and the velocity, the viscous damping by velocity and stiffness by displacement, and again the mass with ground acceleration. So this is ground acceleration and this is the mass acceleration. So we define two parameters here. The first one is the natural period, and the second one is ratio of critical damping. So this is the natural frequency, simply it's natural frequency, and this is also damping. Again, so if we divide this equation by m, we will reach to this equation. And so this is the final somehow equation that we need, the motion equation. And we will use this response spectra. This is not exactly the response spectra, but we can use it for modeling elastic response of structures to earthquake excitation. But a sort of disadvantage of this ground motion parameter is that under intense ground motion structures often behave inelastically, and this is not considering the inelasticity. And the other point is that during the earthquake, the response of a structure changes with time. But the point is that here we are just considering the maximum value. We are not considering the duration of ground motion. We are just picking the maximum values. And so considering these points, when we want to model the elastic response of structures to earthquake excitation, we can take the maximum absolute response acceleration and also the maximum absolute response velocity and the displacement, maximum absolute response displacement. We will extract two pseudo values from these parameters, and one is the maximum absolute pseudo acceleration, which can be calculated using this equation. It's quite straightforward, as well as the maximum absolute pseudo velocity, which can be calculated from here. So when we obtain these three parameters for different periods, we will finally reach to such a graph like that. I don't know if you are familiar with such graphs. They are called tripartite plot or four-axis papers. So here is, you can see these curves here, and they are related to different response spectrum, but for different dampings. Just consider this one, the lowest one. The x-axis, the horizontal axis here is period. The vertical axis is pseudo spectral velocity. This one is also the same, but the units are different. And we have another axis here. I don't know if you can see the pointer. Can you see that? My mouse?
Yes, yes.
Okay, so this axis shows the spectral acceleration, and this axis shows the spectral displacement. So how to read this plot? For example, we are interested in this period. So we will go to the curve of interest with the damping that we are interested in, and we can see the PSV from this axis related to this period, or if we are interested in the other unit, we can read it from here. Then we can use this value as PSA and this value here as displacement, a spectral displacement at this period. Was that clear? Okay, so the next point is that we want to know about data selection criteria, how we select our strong motion data to use it for GMPE estimation. One of the criteria that we can use is based on political boundaries. For example, as I showed you, we have a strong motion network in Iran. For example, we have a strong motion network here in Italy. So they are mainly national strong motion networks, and they are confined in the region defined by the political boundaries. But the problem is that each country is not certainly a simple seismotectonic regime, right? So for example, here in Italy to the north, you have Alps, and you have pole plain, and you have the different regions, but they can extend out of the political boundaries. Oops. So the other point is that earthquakes from one country are not completely different to those in another. So we can somehow combine them, and we will finally usually combine this stuff together to get the results. And the other point is that it leads to a small suite of records with a limited spread of independent parameters when we are just considering a network, a national network in a certain country. So the one problem could be the lack of records. So a solution to this problem is to supplement data sets with accelerometers from other regions with similar seismotectonic conditions. For example, a couple of years ago, the strong motion network in Iran was not sufficient for for estimating a ground motion prediction equations, and they where the researchers were combining and supplementing that data set with those of very well recorded earthquake with California, because they believe that, okay, they are somehow similar. The earthquakes are somehow similar in seismotectonic conditions in these two regions. So this is one solution. And the other problem is that the anelastic attenuation between different areas can be different. And the solution to that one is that it would be minimized by using only near source records. We will get to this point later on, and I'll try to explain it better. So the other data selection criteria is based on seismotectonic regime, which makes sense. And the interpolate, for example, we can consider just interpolate versus boundaries. So we can use the interpolate earthquakes or those that are happen in the plate boundaries. The other example is just to consider the extensional regimes. For example, where the lithosphere is expanding. And another example of such a categorization is to use shallow crustal earthquakes. Okay, the other criteria is based on the source depth. For example, we can consider a maximum depth as a threshold, or we can just consider the earthquakes that we believe that their focal depth is reliable, or we can exclude deep slab earthquakes. Just consider we can just exclude them and consider the crustal earthquakes. And the other one is, which is almost the same, we can exclude deep subduction shocks. For example, some examples of this criteria is to take 20, 30 kilometer shallow crustal events, or we can take 60 kilometer threshold and difference in magnitude definition, or we can consider 90 kilometer threshold, then we will face a large regression error. For high attenuation in mantle, we exclude these deep slab earthquakes because the travel path of the rays recorded by strong motions is sampling the high attenuation in mantle. So you cannot simply combine them with those that are just sampling the crustal structures. Or when we exclude deep subduction shocks, it's because difference in travel path and stress condition compared with shallow earthquake. So these are the motivations behind such criteria for data selection based on depth. So here you can see an example of the selection criteria based on source depth in past ground motion estimation relationships. For example, the criterion of maximum depth is applied by these studies here, and the reason is explained also here. So this is a table, this is the table, one of the paper that I already introduced you, and you can go through that later on. So the other selection criteria is based on minimum magnitude, and here you can see some examples of this criteria. So for example, minimum magnitude selection criteria in past ground motion estimation relationships. This is the same, this is the table from the same paper. And for example, one Airspace 1996 restricted the data to earthquake with engineering significance. So when we are talking about an earthquake of magnitude 2 or 3, they are not very significant from engineering point of view, because even it's difficult to feel such a motion. Or for example, Fukushima 1995 restricted data to earthquake with a smaller errors in the independent parameters. So they just considered the threshold of magnitude 5. And there are some other criterions. For example, Bomer 1998 considered the threshold of MS 5.5. And the reason is that they want to restrict the data with high signal to noise ratio. When you're recording a very small earthquake, your records are not necessarily with a high signal to noise ratio, and they are not actually important from engineering point of view, and they don't also have good quality. So these are the reasons that some studies try to minimize, to restrict their data and select data based on minimum magnitude. And also some of them, just as I explained, they just consider the magnitude accuracy. For example, for one earthquake, you can have different definitions of magnitude, and we will discuss it later on. But it's very important that when you are considering that earthquake and the records of that earthquake, the magnitude should be accurate. So when you understand, when you realize that the magnitudes for this earthquake is not accurate, it's better to just remove it from your catalog, because your independent variable, which is magnitude, is not accurate, and it affects all your coefficient estimations. So the other data selection criteria is based on minimum and maximum distance. So one example is just to consider the distances that are larger than 2 kilometers. The other criteria could be to just take the reliable distances. And what I mean by reliable distances are that the earthquake is well located. So you know that where the earthquake is, where the earthquake epicenter or hypocenter or rupture or whatever is, and you know that where your station is. So you can extract a good measure of distance between earthquake and your stations. Otherwise, if your earthquake is not well located and it has a very large uncertainty, for example, 10 kilometers there, the epicenter or the hypocenter can be 10 kilometers away from where you have where the hypocenter is estimated, then it's better to just throw it away because it will include a very large uncertainty in your estimations. The other criteria is that they just consider near source accelerations to avoid complex propagation effect. We will probably tomorrow discuss this in details, but when you are talking about far field or long distances, you can face some complex propagation effects that we will discuss it later on. The other criteria is just to consider the distances smaller than 200 kilometers. And the reason is that we don't have so many far field data. So it's better to stick with this region, and but we can still study longer periods, but we need usually to use seismometer instead of the strong motion sensors. So here is an example, just to wrap up what we said about that. So we have the earthquake and we have an strong motion network. And when the earthquake happens, it triggers some stations around it, and it may, there is always a chance to lose some information in one station. Maybe the station is not operational at the moment, maybe something is wrong with that, and we will finally select a optimal distance, and we will exclude those data that we are not interested in for the further analysis. Sorry. So the other data selection criteria is based on minimum peak values. For example, we were you are already familiar with PGV and PGA and spectral ordinates. So peak ground velocities. Some studies, they excluded the data with peak ground velocities of smaller than 0.1 centimeter per second. The other is, some others just consider PGA, and here is the table. Then they show, so this is the minimum PGA considered by different studies. And for example, this paper just considered 0.01 as a threshold of PGA. And the reason that explained is that weaker records are not reliable because of resolution of instruments. So they can have different reasons for selection of these thresholds here. For example, here, this study, they selected the threshold of 0.15 to avoid possible bias or so on. So you can, one of the thresholds that you can use is based on PGA, and you can use it as a criteria for your data selection. The other criteria for data selection is based on time history quality. So, for example, you need to have high resolution, high signal to noise ratio in your record. So here are two examples of the low signal to noise ratio, and you have to exclude them from your data set because you need to avoid unrealistic shaking. So when you measure the signal to noise ratio in these two sample waveforms, you will realize that the signal to noise ratio in these two samples are quite low, and you need to exclude them. Another point is that your record, your strong motion record, needs to be complete. So for example, some of the strong motion sensors, they are designed to be triggered by earthquake occurrence. I guess Blaj already told you about that. And so, for example, here you can see an example. The earthquake, the sensor, the station were not able to capture whole the record. So it started recording quite before the earthquake occurrence, so about 15 seconds before the earthquake, and it stopped when about 1 second of the earthquake was recorded. So this, if the recording duration was enough, maybe it was an amazing strong motion record, but we already lost it. And the point is that we cannot just consider this recorded part. We have to throw it away. And the other one is sometimes, I guess this is covered by Blaj lecture already, and you have multiple shock records. So you have a record of this shape, a strong motion record of this shape, but it's clearly, this is not just one record. This is a sequence of earthquakes, sequence of shocks that they are considered, that they are recognized as one earthquake by the instrument. But you need to split them, you need to detect them, or you can just simply throw them away. So the other point is that you can have enough early triggering, that I already talked about that here. The next criteria is based on installation site. So the strong motion stations can be installed in buildings even. We already mentioned structural health monitoring. The strong motion sensor can be on the second floor of a building, the strong motion. So it's quite important to consider that when you are combining the records of strong motion sensors, they need to be installed based on the same installation criteria. The most famous one is called free field. And for example, here you see that these studies have used free field installation sites, and these one have used buildings. So this is also very important, but we usually just use free fields for regional studies or for general studies. The other data selection criteria is based on the minimum number of records per earthquake. So for example, you have one earthquake which is just recorded by one strong motion station. Usually different studies use the criteria of 3 or 2 as the minimum number of records per earthquake, and the reason is to improve the ability of regression to distinguish between magnitude and distance dependence. We will also discuss the details of this one later on. And so the other point is that the quality of your earthquake. So I already told you that we need to consider the level of noise in our strong motion record. And we have different criteria for that. We have low and high cutoff frequencies that we believe that for frequencies less and smaller or larger than these frequencies, our records are not reliable and they're dominated by noise. So these are the examples of the frequency band used by different studies as criteria for excluding the data. For example, the low frequency is selected between 0.2 and 0.5, and the maximum frequency is between 25 and 35 in this study, and the reasons also are selected here and mentioned here, and you can also see that how they selected this frequency band. And so the other point is that we have three axis strong motion records. We have one vertical and we have two horizontals. And the horizontal component is much more important for us. But the point is that when we have these two perpendicular strong motion horizontal records, how should we combine these two components together? So one way is just to take the arithmetic mean of these two components. The other way is to consider them separately. We can consider them both. So we can treat them as two strong motion records. The other way is to take the geometric mean of that, and this is the most useful one. You can take the geometric mean of these two components. You can, I mean, these are all the techniques that have been used by different studies, but geometric mean is the most used one and well-known one so far. So you can also take the largest component. You have two horizontal components, and you will take that one with the largest value. You can also select between these two randomly, or you can take the resultant between these two vectors, or you can take the vectorial addition. But just keep it in mind that geometric mean is the most useful one. So GMPs, or ground motion prediction equations, can be separated into source, path, and site dependence. So when an earthquake occurs, and as I said, it affects our structures, we have one source over here, which is the fault causing the earthquake. And we have a path that the waves, the rays have traveled through this path. And we have also site effects, which is mainly related to shallow structures beneath our sensors or our site of interest. So traditionally, discussion of earthquake ground motion has been split to these three ones: the source effect, the path effect, and the site effect. So here you can see a plane view of a map view of a fault. If you have a fault like that, and you have the profile view, and again the earthquake happens, and it affects our structures, and we, as we already said, we have different effects. So in time domain, the seismic record, what is recorded by our instrument, is a combination of source, time function, path effect, and site effect, and instrument response. And you see that they are convolved to each other, so these are convolutions. But if you take if you transfer it to convert it to the frequency domain, it will be just simply multiplication, and it will be much easier. So we have source, time, and source effect, path effect and site effect. And general equation, a very simple and general equation would be something like that in frequency domain. So to the left hand, you have your ground motion prediction. You have your ground motion parameter in frequency domain that can be amplitude spectra. Okay, response spectra in a certain frequency or period. Then you have your source term over here, and then you have this term, which is geometrical spreading. So these two terms are related to path effect. The first one is geometrical spreading, and the second one is anelastic attenuation. So the anelastic attenuation here, which is shown by K as a function of F, is multiplied directly to distance. But geometrical spreading is multiplied to logarithm of distance. And finally, you have the site effect at the last. So here we will discuss that how we usually characterize this source. It's usually through earthquake magnitude. It's almost the only parameter used to characterize the earthquake source in GMPs. So we have many different definitions of earthquake magnitude. For example, you are probably familiar with ML, and we are not going through all these different definitions, but we will briefly introduce them. I don't know if you're already familiar with them or not. Okay, so ML is usually used by earliest studies, and it's homogeneously determined for a small earthquakes up to saturation about ML equal to 7. And the disadvantage of such ML is that there are not ML estimates available for all earthquake in some data sets, or ML is difficult to predict for design earthquakes because catalogs of historical earthquake often contain unreliable ML. The next type of magnitude is MS, which is far better than ML, and they are somehow equivalent with MW and MA that we will talk about that a few minutes later, in the range of 6 to 8. So we already know that ML is not reliable for large magnitude earthquakes. And the disadvantage of MS is because of the correction for focal depth, estimates of MS are significantly affected for earthquake deeper than 20 kilometers. So the depth of earthquake can bias the estimation of MS. The next one is MJMA, that so it stands for Japanese Meteorological Agency. Maybe they are somehow old-fashioned all today, but it's good to mention them. And the most important one and useful one is the moment magnitude, called MW. And it's the best one somehow, and it's far better if you stick with this one always. But the problem with this magnitude is that it's not usually calculated for earthquake with magnitudes less than 5. So in your catalog, it's sometimes you cannot find the moment magnitude of some small earthquakes. And So this is the main problem with that. The problem with that is that you cannot find it always and for each record that you need it. But otherwise, it's perfect. And when we want to characterize the source, the energy released by an earthquake is exponentially, as you can see in this equation, dependent on magnitude, and the strong ground motion does not increase without bound for increasing magnitudes. The other point is that as magnitude increases, ground motion does not increase at a constant rate. So when the magnitude increases, it's not necessarily the ground motion parameter is not necessarily increasing with a constant rate. So in reality, we can observe that when the magnitude increases, the ground motion increases also with this term here and another term here, which is called magnitude saturation. So an example of this magnitude saturation and its effect on ground motion parameter is shown here. So the curve, so this is distance and this is peak ground acceleration. And the curves with dashed line are just considering the constant shape. But those of continuous black line here and here and here, they're also considering this magnitude saturation term, so the magnitude dependent shape. And you can see that their shape can be quite different from each other. But the point is that in some GMPs, the B coefficient here is statistically insignificant. So the value that you obtain for B in the regression is not statistically significant. And modeling this quadratic dependence here on magnitude requires records from large magnitude earthquake that are not necessarily available. So different other terms also have been used in studies. Some consider M with power of 2.5, or they consider this term, or they consider this term. But the most important point is that when you are estimating the unknown coefficients, you have to take care of that if these coefficients are statistically significant or not. So the other point in characterization of source is that some studies account for source mechanism. So they all need to consider the magnitude, but some of them, they also consider source mechanism. So it means that if the source is, if the earthquake was a reverse as a result of a reverse faulting or a normal faulting or strike slip faulting. And it's quite important because reverse faulting PGA values are systematically higher than other motions like normal faulting or strike slip faulting. And this difference can reach to about 10%. So here you can see an example of the comparison of estimated ratio of horizontal PGA and response spectral amplitudes for reverse and strike slip faulting from different studies, Abrahamson and Silva, and for example, Bohr and Campbell and Bozorgnia and others. So just consider this study of Campbell and Bozorgnia. This is period, and this is the ratio of reverse to strike slip ground motion amplitude. So here you can see that reverse faulting shows significantly larger response, spectral amplitudes up to a factor of 1.5, which is here. It reaches to 1.5. Then a strike slip faulting at short to intermediate periods. So you can see that at period of 0.5, the reverse faulting, the PGA of reverse faulting, ground motion amplitude of reverse faulting reaches to, the ratio of reverse and strike slip reaches to 1.5, but after 0.5 second, it starts to decrease. So it's quite important. It's not a constant line and one, so it means that we cannot combine these two informations together, but we need to separate and include the style of faulting in our equation. But the most important point is that we have to have access to such a data, and if we don't, we need to spend time to collect a catalog of the faulting for our ground motion parameters. So we already discussed this. So when we are considering about the source of earthquake, we already talked about the magnitude. We said that style of faulting can be also important. And another point is that depth of earthquake is quite important for characterization of source effect. So different distance measures can tell us about the depth of earthquake. So these are a list of different types of earthquake station distance measures. We have hypocentral distance, rupture distance, seismogenic distance, centroid distance, energy center distance, equivalent hypocentral distance source, projection distance. So there are many different types of distance, and some of them, they are also considering the depth of the earthquake. So the first one, and I don't know if we have, so the class is up to 12:30, right? You're still there?
Yeah.
Yes.
Okay, I guess so. We have about 25 minutes. So let's skip from this one and go to characterization of path. So we will talk about that later on, but let's say, so when we want to characterize the path effects, the path that the rays are traveling from source to reach to our stations, and this is the distance. This is mainly characterized by distance measures. So the question is that what is the correct distance to use in GMPs? The answer would be the distance from the origin of the actual wave, which produced by the measurement of ground motion. For example, if you are considering PGA or a spectral acceleration, and to the station. So this is if you just read this sentence again, it's not quite easy to determine such an accurate distance for past earthquakes, and for the future earthquakes, it's impossible to measure this distance, this accurate distance. So we have different, as I already mentioned, different definitions of source to site distance. And here we will take a look at those different definitions briefly, and we will somehow consider their effect on our measurements later on. So the first one is the most famous one, the hypercentral distance, which is the distance to the rupture's starting point. So when you have the hypocenter of the earthquake, hypocentral location of the earthquake, you can simply measure the hypocentral distance. Here you can see an example of that. So this is the hypocenter. Just consider this as hypocenter of the earthquake, and this is your station. So the hypocenter means that where the rupture has been started, and this is the hypocentral distance. Here you can see some other definitions of the distance as well, but here you can see that, for example, this is hypocenter and this is your station. So this is hypocentral distance, and here's hypercentral distance shown by red in different fault situations. But just consider, just keep it in your mind. We will get back to this figure later on. But here you have also this RJB, which is a good measure of distance. And just consider the difference between hypocentral distance, which is shown by red, and joiner bore distance, which is quite smaller here. Okay, the next and the simplest measure of distance is epicentral distance, which is the horizontal distance to the horizontal projection of the rupture's starting point. So the rupture starting point is the hypocentral location, and when you just project it at the surface, and this will give you the epicentral distance. So one of the disadvantages of this epicentral distance is that it doesn't consider depth at all. And we already discussed that, and it turns out that the depth is quite important. So in this case, just imagine that your earthquake hypocenter is not here and it's here. It's quite deeper. So it has the epicentral distance stays unchanged for these two earthquakes, and it doesn't have any information about the earthquake depth. So the other definition of distance is called rupture centroid, and this is the distance to centroid of the rupture. There are so many different definitions, but I'll finally tell you that which one are the most important one. And you already know about hypocentral and epicentral distance. So this is the distance to point on the fault rupture where energy considered to be concentrated. So it's almost similar to rupture centroid distance that we introduced. So this is one of the most important definitions of distance, called surface projection or joiner bore or fault distance. So in literature, you may face one of these names, joiner bore or fault distance. And this is the distance of the surface projection of the rupture plane of the fault. So here, your fault is vertical, and this would be your joiner bore distance. Just to recall the definition, this is the distance to the surface projection of the rupture plane of the fault. So for a vertical fault, the R joiner bore distance is similar to one of the other distances that we already introduced. Can you tell me that which one is that? In this case, this is our joiner bore distance, and this is similar to another type of distance that we already talked about. Can you tell me that which one is that?
I think it's the epicentral distance.
Yeah, it is, exactly. So, for example, here we have dipping fault, and this is hypocenter, and this is the hypocentral distance, and this is the projection of the rupture on fault, and this is the joiner bore distance. And then another interesting point is that sometimes on a dipping fault, the station is located within the area of the surface projection of the rupture on the fault. So if you project this rupture shown by rupture on the fault, which is shown by thick line here, it would be from here to here, right? And the joiner board, the station is located on top of that. It's inside that. So the joiner board distance would be 0. So far, hypocentral and epicentral distances are the simplest one, and the joiner board distance or fault distance is somehow the most well-known measure of distance, and you need to remember about them. So the other one is seismogenic depth, which is somehow sort of old-fashioned one. So this is distance to seismogenic rupture surface that assumes that the near surface rupture in sediment is not seismogenic. And so here you can see that this is the seismogenic depth over here or over here. So just this is hypocentral distance, and this is seismogenic distance shown by red here. So the next one is rupture, which is source or fault distance. This is also a good measure of distance, and this is the distance to rupture surface. So, for example, here you have a vertical fault. Okay, so you have a vertical fault here, and the rupture is shown by thicker line. So this is hypocenter, and the rupture, the surface rupture is occurred here. So this is rupture distance. And surface projection with focal depth is the other one. Distance to the projection of the rupture on a plane at the focal depth. So, and I guess this is the last one, mean of distance to, so elliptical distance or average size to rupture n. So it's a complicated one, and this is not one of those important measures of distance that you need to keep in mind. So the other one is equivalent hypocentral distance. So too many boring definitions, but how these different distance measures can affect our ground motion predictions. This is the most important point. So these are the map views, and we have a fault plane, which is shown by this rectangle, and it's about 50 by 20, and its deep is 30 degrees, and we assume that it's corresponding to an earthquake of magnitude 7. And you can see the surface projection of the fault here, and the hypocenter is located here at this corner. So where the rupture starts. And these colors are corresponding with different definitions of distance. For example, this yellow one, I don't know if it's yellow or what. So it's epicentral distance. This is surface, this is joiner bore distance, this is rupture distance, and this is elliptical distance. So as you expect, when we are considering the epicentral distance, these iso distance lines are circles, and their center is epicenter. When you consider the surface projection or joiner bore distance here, your iso distance lines would be something like that. When you are considering rupture distance is like that, and when you are considering elliptical distance is like that. So in case of epicentral distance, your iso distance lines has nothing to do with the fault. Even so, just consider that the fault is not here and the fault is here. I don't know if I can plot something here. Just imagine that this is your fault plane. The epicentral distance has nothing to do with that. So there are so many important information about the fault which are missing in epicentral distance. But you see that joiner bore distance here, it's somehow the distance, iso distance is somehow mimicking the fault plane very well. And also the rupture distance is affected by fault plane, and it contains some information regarding that. So in that case, you can realize that somehow epicentral distance is not a very good measure of source to site distance, because it's not, it doesn't contain any information about depth or rupture plane. And that's why joiner bore distance is one of the most famous one, and also rupture distance is a very well-known measure of distance. So we reached to characterization of site, just to recall that what we were talking about. I guess it was too long for you, but we already discussed the source effect, we already discussed the path effect, and now we reach to the site. So this we discussed the magnitude, different definitions of magnitude, style of faulting and its effect on ground motion parameter. We also considered path effect and distance, and how different measures of distance can affect our ground motion prediction. And then the final one is characterization of site effect. So local site conditions at accelerometer stations can dramatically affect the strong motion records, and intermediate and long period spectral coordinates can be significantly affected by local site conditions. There are the different techniques have been used by different studies to incorporate site effects into a GMPE. So one of them is the simplest one, and is to use records from similar site condition as a data selection criteria. So if you remember, we discussed different data selection criteria. And one way to incorporate site effect into a GMP is to adopt a data selection criteria based on site condition. So different types of site conditions can be categorized. For example, we can consider a stiff clay, we can consider soft soil sites or bedrock sites or deep soil sites or rock sites or rocks with VS values of more than 750 or basement rock sites. So when you just consider one of these site conditions and only use those records of this site condition, so this is the simplest thing that you can do. The other option is to use records from different site categories. So these are different site categories, and you can also find different definitions for that. But when you use different site categories, you can perform regression on subsets of records with the same site classification. So you put all those with the basement site condition together and those with soft soil sites together and apply the regression on those. The other option is the advantage of this method is that somehow nonlinear soil behavior is implicitly included. And the reason is that the magnitude of distance scaling for each of these site categories independent of that for the other categories. When you are just considering this one together and this one, all the records of this site together. The other method is to use multiplicative factors between ground motion and one type of site and that of another. You can just simply consider the basement rock sites or rock sites with high shear wave velocity values as a reference, and then estimate the other ground motion predictions on the other sites and with a multiplicative factor with the reference sites. So the next would be analysis technique, and I guess it's better to continue it in the afternoon. I guess you are. What do you think, guys?
Yes, let's continue it in the afternoon.
I guess you're already sleeping, right?
No.
Who is awake?
No, sir.
At least. Okay, so perfect. Then we will meet again. I guess it's at 1 or I don't know. Just recall me.
At 2, please.
2. Okay,
Yes.
perfect.
At
We have
2.
time for lunch.
Yes.
Okay, so see you then.
Okay.
I couldn't.
Oh, sorry. Yeah.
Sorry, I couldn't introduce myself because of my computer problem. I couldn't open the microphone of my computer.
Okay, then do it now.
It's okay. I'm with Innocent. I'm doing Masters of Geophysics in Rwanda. Yeah.
Oh, perfect. Nice to
Okay.
meet you. Okay, guys. So see you again at
2.
2.
Yeah.
Great.
Bye-bye.
Okay. Bye for now.
Thank
Yeah.
you.
Bye.
Bye.
Morning.
Yeah, see you. Bye.
Morning, Tarek.
Yeah.
Innocent. Prof. Karim has sent an email.
Yeah. I've seen it.
Me, I'll
Really?
choose Zoom I'll choose on Zoom.
But by the way, I think that you, Tarek, are not in the.
Tarek, your name is not in.
Is not in the schedule.
Schedule.
So.
Let me just see.
Oh, you are not feeling. You are still not feeling well.
Yeah, I told them that the medication that I'm taking,
maybe.
they are perturbing me. Maybe they rescheduled it for me, I think.
Yeah. Then
Okay.
I think maybe that's why. Yeah, because I didn't see your name.
Okay. Just I will see. Just let me time to see. Okay.
Simone and Innocent, what will you choose? Like in presence or Zoom?
I don't know. I think that
Guys,
maybe I will choose in presence.
No,
Presence
maybe I like
better.
Innocent. What do you want?
So for
Do you
Innocent,
think that I have any
Innocent
other
and
choice?
Foxa,
I
they don't
can't
have the
even
choice.
Is that?
I'm saying
Innocent
that
and Foxa, they don't have
I'm
the
not
choice.
having any other choice.
Okay, yeah. For you, you have to choose Zoom. Yeah. He said it in the email, but for us, he was asking us that what we want. I think he has scheduled the time already, and he wants us to choose whether on Zoom or so.
Yeah.
For me, I will tell him on Zoom. I think with that, I will be comfortable then.
Yeah, but I don't know.
And he said it will not be like open. It will not be kind of open, or he said we shouldn't interact.
Yeah.
Yes.
By the way, I checked the other day the recordings that the ICTP puts on YouTube, and every time we speak after the lesson, it's recorded.
It's recorded.
We are on YouTube. Yeah.
Okay.
Be
Cool.
careful on what you're saying.
Yeah, it's true.
Yeah.
Yeah, we will not interact. We shouldn't. I'm the first person though. I am the first person to do my exam.
Yeah.
Yeah.
But I mean, maybe it's better that you're first, because
Yes, I always choose the first person. I always choose the first.
Gentlemen, can you hear me?
But I think also you like it.
Hi,
Yakubu.
can you hear me? This is the video team.
Yeah. We can hear you.
Since the lesson is finished.
Okay.
Yes.
Because otherwise you guys are gonna go on YouTube.
Yeah. We know.
All right.
Thank you.